Okay, well, welcome back everybody to day 2 of the Postdoc Symposium. I'm not your host, my name is Mike, and I work here in CRD. I'm a postdoc in the Data Analytics and Visualization group. And I'm gonna be talking about a project that I worked on over the summer that was quite exciting, I think is interesting. It's got a complicated title, but really what it was about was interpolating in between images and finding how do you deform one image into another. Oh, yikes. So for some background, I work directly with experimentalists that are at the Advanced Light Source. These guys are taking X-rays, these guys and girls are taking X-rays generally of small things. Those are materials. So in particular, they're looking at materials under extreme conditions. So this is somebody I work with. This is Harold. This is an actual scientist rather than a mathematician. And he's holding a sample of rock, or specifically a meteorite from NASA. And next to him, he's got his chamber that can hold on to this rock and crush it, as well as apply incredible heat and take X-rays at the same time. So you're able to subject these samples to extreme conditions and loads and find out what the microstructure of the fracture mechanics looks like in real time with high-resolution images. So formally, this is called microcomputed tomography, but you can also just think of it as X-rays of small things. So the problem, and the reason that I'm involved and CRD is involved, is that these images are big. So each image, when it comes out of the X-ray machine, is around 14 billion voxels. If you save that as floating point, it's 55 gigabytes. Even as saved as 8-bit unsigned int, that's also 13 gigabytes. And experiments can generate tens to hundreds of them. So very rapidly, you can find yourself in the terabyte or tens of terabyte range just from a single scientific question. So when you have that kind of data and that kind of velocity, there's two kind of questions you would like to be able to do. There's A, can we get better data? And can we analyze this in some way? So one thing that happens, especially when you're looking at images, is that you try to naturally look for correspondences. So we have this rock within the rock on the left, and we've noticed that on the right, it's cracked. And this kind of tracing, or finding out how one image turned into the other, is something we do naturally and can also help A, guide experiments, and B, let us analyze them. So that process, that problem, is called digital volume correlation in the material science community. In the medical imaging community, that's called image registration. So the object that we're interested in is this deformation field. So deformation field is given by this variable phi. And we have our first image I0, and we assume that in I1, we have the exact same material, but now it's undergone some deformation. So every point x in I0 corresponds to some other point in I1, y, which is x plus some kind of deformation. And to recover that, we pose an optimization problem. We would like to find some deformation field, which carries I0 to I1, such that it satisfies some loss function, as well as some constraints. So you don't want to just assign this in any which way. You'd ideally like this deformation field to be smooth, and you'd like the distance measure to encourage these two images to be as close together as possible. So as I mentioned, this is something that we're interested here in the lab, but also just in the community at large. This is increasingly becoming a basic tool in the material science and mechanical engineering toolbox. So in particular, there's now commercial packages which offer it. So there's Aviso, which we have at the top. And at the bottom here, this is the number of papers that are citing articles with the keyword digital volume correlation. So I'm not sure if it's an exponential or a high order polynomial, but this is a tool that this community is using and is using increasingly frequently. So our argument, of course, is that the existing software is inadequate. So there's really only two ways that you can go about this. There's various sub-ways that you can try to solve it, but this image from Van Dijk et al. Illustrates it very well. Suppose you have two overlapping subvolumes of this first image of a lion, and part of the lion you'll notice is out of view. And now we shift the lion so that he's in view, and that's what you see in the two images to the right. If you're doing what's called local digital volume correlation, you treat the green box and the blue box as independent, and you try to find where is their best match in the second image. So that's this local approach that we see here. And what stands out is that you don't get a very nice continuous deformation field. That's obviously very simple to parallelize, but you don't get a very desirable result. On the far right, what you see is a much more smooth or continuous deformation field. So now that overlapping subvolume remains consistent. It should be the same. However, there are no, as far as we know, HPC implementations for this kind of problem. So you have to trade off. You can either get global information, and you're not able to run it on full resolution images, or you can get local information and run it on whatever image you want. So our idea is relatively simple. There's an area out there called optimal transport. This is borrowing ideas from mathematics. And in particular, there's recent work on scalable and parallel solvers to solve this problem. So we're going to frame image deformation or digital volume correlation as an optimal transport problem. And then we're going to exploit these scalable and parallel solvers that exist to handle it. So for some background on that, digital volume correlation, sorry, we're past digital volume correlation. We're at optimal transport. So optimal transport is a model from mathematics, which is how do you, at least cost, transport all mass from one density to another. So if you look at the bottom image here, you have a star, and you have, at time is equal to 1, 2 circles. And the question is, at the least amount of cost, how do you transport one from the other? And this is an interpolation that you would get. Similarly, this has already been used in image registration problems already. So we wanted a model that would be accepted by the community that we can defend easily. So at the top, you only have these first two images, image 0 and image 1. And every image in between is an interpolation from optimal transport. So there's a very natural and accepted model of image deformation. And this is what it looks like. So before, we have our image I0 of x. And we're going to assume that at point x, we have a certain amount of mass, which is proportionate to I0. So we assume this big cayenne blob here has a specific amount of mass, and that the green mass over here has the exact same amount. So from the point x, we're going to be transporting a certain amount of mass to every other point yj. And this can go anywhere it wants in the other domain. We're going to eventually define our deformation field as the weighted average of them. But what we'd like to solve for is p, or this is called the transportation plan. And that dictates how much mass from the point x gets transported to the point yj. And the linear program looks like this. The constraint set is that all mass from image 0 is transported to image 1. And the cost function here is we would like to do that at least cost. So we would like to go the least amount of distance, carrying the least amount of material. So if you recall the size of these images, n in this case is the number of voxels. So for full resolution images, this is 1 to 10 billion. The one that we've been looking at is around 14 billion. So if you're trying to store a table that tells you how much mass goes from each point to each other point, that's quadratic. That takes 10 to the 18 points. That's just far too big. That's something that Corey would sweat on. The other issue is that standard LP solvers for this kind of problem scale poorly. So they scale as you go n squared or they go n cubed at the worst. So in other words, size is a big problem. And we need to either reduce that for our storage as well as our runtime. Oops, sorry, I'm jumping ahead here. I'm also moving kind of quickly so I can figure out a way to slow down a bit. So if you haven't seen this work, it's really exciting recent work by Marco Couturi. And the idea is instead of solving the sharp linear program we were looking at before, you add an entropy regularization term. So that's this term here, Pij log Pij minus 1. If anything, that doesn't look like it helps at all. You've added a nonlinear term to what was a linear program. There's two benefits. The first is that this remains a convex problem. And the second is the following. You can show, if you take the optimality conditions, and here you kind of just have to trust me, you've now reduced the problem to linear storage. So in particular, P now takes the following form, where you have a diagonal of U, a known matrix K, and the diagonal of V. So this known matrix K is an exponential, and U and V are both an Rn. So U and V are the same size as our original image. So we've taken what was a quadratic problem and now reduced it to linear storage. Well, I didn't. Marco Couturier did, and we're going to be using that. So what remains to solve for? We know our form for P. We don't know what U and V are. And this is the algorithm to do so. It's 3 lines in math, and each update ends up being a multiplication by this exponential matrix and an element-wise divide. That multiplication by the exponential matrix is, if you recognize it, a Gaussian convolution, which can be implemented. You can argue that it's n log n, but really it's n. And this is what the implementation looks like. So we used a high-level HPC package. This is from Dmitry Morozov, a collaborator. And if you're using any kind of big data, I highly recommend it. The entire implementation, this is the main loop, takes 20 to 30 lines for a linear program that just a couple minutes ago, most supercomputers would struggle to fit. So how does it do? That's what we're much more interested in. This is the data set. These are the meteorites that we were looking at before that Harold was holding. So at the bottom, these are the real original images. And at the top, we have these kind of funny scrambled images. So we took 2 images and we scrambled them in a particular way so that we had at least some ground truth to unit test our algorithm and see how it's doing. And this full resolution image, we try to get an idea of how is our algorithm scaling. So as far as quality of the deformation goes, for our, albeit very simplified and very synthetic example, this passes our unit test. So it provides a acceptable deformation. In terms of scaling, once we scale this up to 8,000 cores, this is now fast enough for something that you can use in an experiment. So if you're able to compute this deformation field quickly, you can go look at a point of high strain. And 3 minutes is the rough turnaround that you would want to be able to do that in. So what does the final result actually look like? Here's 2 images from the meteorite. The first one is unloaded, and the second one has been loaded, and we still have that crack that we were talking about before. And this is the amplitude of that deformation field. So if you were brighter, you moved over more. At this stage, we're kind of struggling to interpret this. We noticed that there was big movement up at the top right, but it seems like what we're capturing right now with this algorithm is just bulk movement of sub-rocks in a different phase moving around, rather than fine stuff like cracks, which is what we're after. However, the final result, we're still able to compute this map for an image that was 14 billion voxels. The final deformation field took up, I guess I don't have it up, there was 275 gigabytes, and it brought attention to rocks that are shifting around. So something that's a little bit more promising, we're still working out some bugs here with boundary effects that we see at these bright spots. But here's another experiment that's happening up at the Beamline. And in this experiment, they have an instrument at the top, which is also crushing a rock. Crushing rocks is a theme with this team that I work with. And this, at the bottom here, is the deformation from image 1 to image 2. And you can see the algorithm picks up on the fact that this crack has enlarged a little bit. And then you don't really need somebody to tell you that it's now fractured and there's a bunch of cracks here, but this algorithm still highlights where those have taken place. So you have a high displacement field where there has been high displacement. So I think, like everybody else, I went a little bit quickly, but as a quick summary, I think we've made the work isn't finished. There's a lot of validation to do and a lot of experimental work to make sure that this would be useful for a scientist. But I think we've made a real dent in this problem of scalable and global digital volume correlation. So we've demonstrated scale up to 8,000 cores. However, there's several issues. So we'd like for this to be something when they look at this large image, they see something that they immediately want to go look at. And furthermore, on the mathematical side, there's several issues surrounding numerical instability, but we think there's routes for getting around that. So of course, this didn't just happen by myself. Danny Yoshizima is my supervisor here. Dmitry Morozov helped me quite a bit with the HPC implementation. Harold and Dula are the experimentalists, and I thank Francesco Panerai, formerly of NASA, now with UIUC, and Marco Voltini here at LBL for their data. And I thank you. for paying attention. Hey, how's it going?
Thank you for your presentation. Very good work. My first question is, so if I understand well, you can do a run in 5 minutes with the 8,000 calls to have your results?
Yes. Yeah.
So you need the 8,000 calls for like reducing the time to 5 minutes, but do you also need them for the memory footprints?
Oh, no, that's a good question. I don't believe so. I think so the memory footprint of the whole problem is about 400, 500 gigabytes. So I don't think I can't remember how many nodes that ended up being.
Okay.
Yeah.
So it's mainly because of the time consumption. Right?
That's right. Yeah. Yeah, what's up?
Could you go back a few slides?
Of course.
A lot of slides.
Yes, which one?
To the one where it shows like one pixel going to like several others.
Yes, of course.
Yeah, so if I understand this correctly, because this is so outside my area of expertise.
That's right.
So for every pixel it's every voxel.
Yeah, that's right.
So every voxel. And so are you associating this single voxel with basically trying to see where it goes in all voxels in the other volume? Or
That's
just,
right.
just that same layer?
No, all other points in the image.
So basically trying to associate, like, so for every voxel in the original one, there's basically an association with every voxel.
That's right. Yeah. That's right.
Could you go to the next slide? I guess this one and the next one. Could you expand a bit more on how the problem scales down from an n cube to this PEL?
Yeah, absolutely, sure. So it's I think I kind of breezed through it in this slide, but it works as follows. So you add this entropy term here, and there's a regularization parameter that I just forgot. And for these two constraints, you have n constraints for each one, right?
Yeah.
So if you take your Lagrangian, so you introduce your dual variables, and you bring that up from the optimality conditions, these are your dual variables, right? U and V. Well, K, we already know. It's this exponential. Cool. So the only thing we need to find out is U and V here. So we substitute those back into our constraints.
So when there's a problem then reduce, you could still do the same thing, right? Like you could still apply this process.
Sorry, excuse me.
You could still apply this process even with your quadratic objective that you had in the beginning.
Sorry?
You could, in the previous slide you told that this problem scales up with n cube or something.
Standard LP solvers do, yeah, that's right.
Maybe I'm not getting this. Being a quadratic programming problem, I don't understand the problem.
Oh, it's a linear program.
You have a quadratic program.
Well, it's quadratic in xi and yj, but those are known. So it's linear in pij. Pij is what we're solving for.
PI is okay.
Yeah, that's right.
Sorry.
No worries, yeah.
On your conclusion, you also.
Sure, sorry. So the question wanted to illuminate how the n cubed worst case now became a linear algorithm, and I believe I answered it.
So in your conclusion, you're talking about some numerical instability.
Yes.
Could you talk a bit more about that?
Yeah, absolutely. So this particular problem is known to, so there's a regularization parameter that I'm missing here, which is a sigma. We added this entropy term, right? Ideally, you want that regularization to be as small as possible. And what ends up happening is, in this iteration here, you end up dividing by 0 at some point. So there's strategies to mitigate it, and we implemented most of those. But there's also a larger issue here, which is that you have to have all mass from image naught go to image 1 as a hard constraint. So otherwise, this is an empty set, and this algorithm won't apply. So one thing that we're looking at doing is loosening that up. Like, all right, well, not everything needs to get transported over. It can just be close enough, right? Yeah. Sorry, I don't know if that answers your question, but
Yeah.
okay.
Is this code open source?
Yes, it is. Yeah, it's messy, but we plan on releasing
There
it.
are some smaller tests, like if we want to try it on one node.
Yeah. I can. Well, we have to go to the IPO office, but then, yeah, you can absolutely try it. Are there any other questions? Okay, I think Joe's up.